My favorite ride at Disneyland, I don't know why, I get a kick out of it, is Mr. Toad's Wild Ride. How many of you ever been on Mr. Toad's Wild Ride? It's just so bizarre. And the name is pretty cool too. So I thought, well, if I was going to design a roller coaster, what would the roller coaster be like? Well, my roller coaster, because I'm a physics teacher, my roller coaster would have no friction in it whatsoever. No air resistance. And the only forces doing work would be springs and gravity. So consequently, mechanical energy would be conserved. So here's how it would work. Imagine, here's the ground right here, level ground. And here's the track. You would get on right over here. Here's my little roller coaster car. And here you are in your roller coaster car with your arms up and all excited, ready to go. And then the track looks like this. And then it comes down like this. And then it goes up like this. And it goes down like this. And then over here on the end is a brick wall. I didn't say it would be a popular ride. Now, of course, I don't want people to actually slam into the wall. That would be an inelastic collision, as we're going to talk about here in a few minutes. What I want to do is put a little movable barrier right here connected to a very efficient spring. And so what will happen is the spring will get compressed and then it will uncompress and push them back. Now let's take a look at this in terms of energy, what we've been talking about. When you're at the bottom of this ride, you have no height. And we said that gravitational potential energy is the energy stored in an object because it has height. Well, it doesn't have any height, so it has no potential energy. Also, it's not moving. And if it's not moving, it doesn't have any kinetic energy. Kinetic energy is the energy contained in an object because it has mass and it's moving. Well, it's not moving. So it has no energy, and there's no spring attached to it, it has no elastic potential energy. So these people have no mechanical energy compared to the ground right here. So what you have to do is you have to give it energy. Somebody's got to do work to drag these people to the top of the hill. And that's, what a generator's for. So let's say we've got a little, gasoline-powered motor that's hooked up to a chain. There's a sprocket right here, and there's a chain that's hooked to these people, and and it drags them up all the way to the top. And you've been on a roller coaster before, right? You know how they except for California Screamin', which is my favorite roller coaster, because they do it a different way. But on most roller coasters, what do? They drag you, they pull you all the way up to the top of the roller coaster, and then they release you. Well, somebody's got to do work to get you up there. So what happens is that they drag you all the way up here until you get to the very top. So here the people are at the top of the hill. Very exciting. Okay. Now the object has mechanical energy. And we're going to release them. And the only force that's going to do any work is going to be gravity, or the component of gravity that's parallel to the track, until it hits the spring. And then the spring will do work. It'll apply a force through a displacement on that object. And so we're going to say that they have energy up here. And I'll call this E1. Yeah, thank you. There you go. Take that off for me and just put this right there. Thank you. Okay, then they're going to race down here and to get to the very bottom. Now, where is all the energy? See, somebody did work, dragged them to the top. And now I'm going to say that the only forces doing work from now on are gravity and this spring. Thus, mechanical energy will be conserved. Where is all that mechanical energy at the bottom? It's kinetic energy. Now let's look at them right here. We'll call this E3. Now the 1, the 2, and the 3, it just refers to which, when are we looking at the roller coaster. I'm just going to call this arbitrarily position 1, position 2, position 3. I can pick any position I want and give it a number. And then let's say that this is the compressed, maybe that this barrier is all the way out here and it gets compressed when they hit it. And so here is our thing, and here they are all thrown forward, getting a little whiplash or something as they're compressed against that spring. And so the spring did work, took away their kinetic energy, and now it's just elastic potential energy. We'll call that E4. Oh, but let's talk about E3. Does the roller coaster have height? Yes. Thus it has what kind of energy? Gravitational potential. But it doesn't have as much gravitational potential as it has had up here. So where is the missing gravitational potential energy? It's still in the car as what? Kinetic energy. So at E3, the energy is being shared between kinetic energy and gravitational potential energy. But when you add them together, you get the total amount of energy we started with. And so conservation of mechanical energy says that if the only forces doing work are gravity and springs, then you can say the mechanical energy at 1 equals the mechanical energy at 2 equals the mechanical energy at 3 and equals the mechanical energy at 4. So we're saying, look, the mechanical energy doesn't, the total amount doesn't change. At least once you start at the top. Now, it did change to go from here to here. And how did that happen? Somebody did work. This little generator right here burned some gasoline, or maybe it's an electric thing and it pulled energy off the grid or something like that and pulled them to the top. Gave them mechanical energy. But once they're released, they do that. Now, well, what kind of mechanical energy does it have at E1? Well, it has no kinetic energy, it's not moving yet. But it does have gravitational potential energy, and since this is position 1, I'll just call this H1 to stay consistent. And so I'm going to say this is mgh1. Now look at E2. What kind of mechanical energy does it have at E2? Kinetic. So it's 1/2 the mass times the velocity at position 2 squared. And again, this subscript 2 just refers to this position on our little chart here. Now here's the one that's a little bit different. Look at E3. the mechanical energy at position 3? Well, it has height, doesn't it? We'll call that H3. So it has mgh3. But it also has kinetic energy. Plus 1/2 mv3 squared. And then, of course, it has at E4, I'm just going to call it E4 for right now because we haven't written an equation yet for elastic potential energy for a spring. And so we're not going to worry about that right now. But do you see that this gives us an equation that we can solve for unknowns? If you know the height that you started with, you can figure out the velocity at the bottom of the hill, can't you? Just take this and solve for b. Or what if I know this height, and I know this height, and I want to know how fast am I going at the top of this little hill? Well, it's a little bit more algebra, but you just set this equal to all of this and solve for v3. And here's the beautiful thing about it. We're not using kinematics anymore to find this final velocity. We're only using energy. And look, this is not an inclined plane in that it's not a plane. It's a curve. But it, so the acceleration is not constant. So we can't use the kinematic equations. If you tried to draw a free body diagram and figure out the forces on this thing, well, those forces vary. The acceleration varies. It's so complicated. You can't use force and kinematics to figure out these velocities. But you can use energy, and energy makes it easy. Energy doesn't care what happens to the roller coaster between here and here. I mean, I could put a loop-de-loop in here. Woo! Okay? And as long as we say there's no friction doing work that's taking mechanical energy away, or air resistance, and there's no motor on here to accelerate or anything, we can figure out, once it leaves here, we can figure out how fast it's going anywhere at any height. Or if I knew the velocity, I could solve for the height. Or if I knew what velocity I wanted at this height, I could figure out, well, if I'm designing a roller coaster, solve for h1. How high do I need to start? So if you're a roller coaster designer, you can use these equations to at least get a rough idea of how high you need to start. Now, in a real roller coaster, what have you really got? You really got a little bit of friction, but not a lot. This gives you a good first approximation of how your roller coaster will behave as it moves through it. Okay? So in many of the problems that you're going to work, this is how you start. You say, okay, the energy at this position will equal the mechanical energy at this position if gravity and springs are the only thing doing work. And actually in the problems you're going to be working, it's all gravity and kinetic energy. We're not really doing springs, at least not yet. So you would say mgh1 equals 1/2 mv squared, or 1/2 mv squared plus mgh3, or whatever, depending on what they're asking for. And it's a very handy way to solve problems.